All right, are there any questions? Otherwise, huh? Yeah, go ahead.
I was wondering what's the schedule for the presentation?
Oh, yeah, I'm going to get to that. Yeah, I'm glad that you asked me that question. Right, but let's see. Okay, the schedule for the presentation, right? That's the question that you asked. Okay. Now, so far, I have received, let's see, 1, 2, 3, 4, 5, 6, 7. Okay. I have received, emails from 7 people with, with titles of their papers, okay, and what they want to present. And I have said it's okay with me in each case, okay. So I think that presentations, we would like to start them next Monday, this coming Monday, okay. I'm getting done. In fact, today itself I can finish the course, but I'm going to give one more lecture on Friday, okay? Because, there has been some development since this material was developed, so I'm going to give another talk on Friday, right? About some of the latest things that are going on here, okay? Or at least that I'm involved in. So the presentations can start on Monday itself, Monday that is November 17th, okay? Now, I was going to ask the people who already, got the titles of their papers approved by me, all right? Whether they are ready to present on Monday, We need 3 people on Monday, then 3 people on Wednesday, okay? Then another 3 on Friday, okay? And it'll continue instead of the regular, because see that way, how many people were planning to be here in class for the 26th? Okay, I'm thinking that 26th is the day before Thanksgiving. Okay, you want to be here? Okay,
I will be here.
okay. No, but I'm just saying that I know in my undergrad class nobody's going to come. I'm going to ask them because that class is from 1:50 to 2:40. The day before Thanksgiving, nobody will come. All right. So I'm going to ask them, and I'll probably give that day off. All right. So now here, see, like if we start on Monday, if you include the 26th, then you have 7 lectures. Okay. If you leave the 26th out till December 3rd, I think, what is the last day of class? Huh? Oh, then we have classes after that. I was thinking I'll wrap it up on the 3rd itself. Okay. So that way there are 6 classes, all right? 3 people are presenting each day. We have 17 people, we get done. I mean, you don't have to present on Monday because I'm sure that, or I'm hoping at least the people who got their things approved, they will volunteer. Okay. So, yeah, but I don't want to leave an empty slot. And the 26th, I don't want to do, I'm not particularly keen on doing the class because probably in the morning I will also go out of town. Okay. So I have to be back in time and plus it's the day before Thanksgiving. All right. So, uh, unless
So do we have class the day before Thanksgiving? I mean,
we don't have to have the class, okay, unless you say that's the only day you can present, so yeah, because yeah, the if we start on Monday, okay, so the next week there will be Monday, Wednesday, Friday, okay, so there are 3 lectures, all right. Then the following week, the Thanksgiving week, there'll be 1 lecture. We don't do the Wednesday class. And then the week after that, right, that is the week of December, what is it, 1st? So December 1st and December 3rd, we can finish it off, okay? And she's saying that 9th is the last day. I didn't know that, okay? Because my other class also, they're taking their last exam on the 3rd, okay? I like to get done a little bit early, all right? I mean, and people want to travel. Somebody asked me at the beginning of the semester and all that. I said by December 3rd, the story is over, basically. Okay. But I'm just saying, if we take the 26th off and then it's a problem, if we need to, maybe we'll meet again on December 5th or whatever. I mean, what is December 9th? 9th is a Tuesday, so December 8th is a Monday. Okay. Yeah, if we need to, okay. I mean, we can go into December 5th and December 8th, if we need to, because, of course, you'll do the work, okay. I'll just come here, that's all, right? I mean, because you're the ones that'll be presenting then, okay. The role is going to change. Like my work is just grading and evaluating after this Friday, okay. So, I mean, December 26th we don't have any class. Is that okay? Or okay. So we are not going to meet on December. I'm sorry, not December 26th. December 26th we don't have any class anyway. November 26th. Okay. So no class on November 26th. That is the day before Thanksgiving, right? And so among the people, all right, are who have already gotten their papers approved by me, who are the people who are prepared to present on Monday? Okay, starting on Monday. Like I need 3 volunteers for Monday and then 3 for Wednesday, to get the thing started. Okay, good. Okay, so you are Monday, that is November 17th. Okay, fine. Who else? All right, what's Ahmed Al Kawan? Okay, good. and make your presentation so that, whatever you do, right? Remember, this is a 50-minute class, okay? So shoot for like between 15 and 17 minutes, okay? Because I have to go to that building for another class after this, okay? And, there's only a 20-minute break in between, right? So don't make it too long, right? Like make it like about 15 minutes, maybe 2-3 minutes for questions, and then we go. So then I need one more volunteer for Monday, right? No volunteers, okay. Or, right, let's see. Is Siamak here or no?
I have another presentation on Monday.
Oh, really? Okay. But in what class? In what class? Which class?
Classical biological analysis.
Oh, okay. So he's driving you crazy, huh? Okay. All right. Then let me see. See, I'm not. I need one more person because we don't want to leave. You can do, okay. Well, let's see. What was your? But you didn't even pick a paper. You picked a paper? Okay, then I didn't write it down. So there are 8 people then. Okay. So what was the paper that you selected? Oh yeah. Okay. Combinatorial drug optimization. Yeah, that'll be good. On Monday it will be good because I will talk a little bit about not that paper, but about the work that we have been doing on combinatorial selecting the optimum combination of drugs. So I will talk a little bit about that on Friday. So that'll be good. So that is for next Monday, all right? What about Wednesday? Okay, so you are Siamak is Wednesday, so November 19th. Okay, I need 2 more for Wednesday. Yeah, go ahead. Ali Reza is also there. Good. And then 1 more. Okay, good. Okay, so Shabnam is November 19th. Okay, right. And then for Friday, let's see, 1. But Friday we can fix later. But there are 2 other people, Sajad Zadeh and yeah, yourself and Huang Tran. I don't even think he's even here. He's probably at a conference. But I'm saying for the others, you need to, you at least got some time, okay? Because some of your friends volunteered, right? But be prepared, like either next Friday or Monday after that, or talk amongst yourselves, and figure out, right? But I just don't want empty slots, because we want to get stuff done together so that everybody can finish their business and go on their way, So, okay. So just start looking at something, send me an email, I will respond right away. And most cases it's at least so far all the people that selected papers, those are fine. I don't have any problem with them, right? So yeah, we will get started on Monday itself. So with the presentations. So any other questions? Okay, so yeah, today we are going to talk about external intervention based on optimal control theory. Right? Last time we discussed, intervening in gene regulatory networks, and through that simple example, we tried to study what would happen if you perturb a single gene. Okay, how can you perturb a single gene so as to reinitialize the genetic regulatory network and get its states moving, right? Or restart it from a more desirable position. Then after that, we also looked at the possibility of changing the truth table of the genetic regulatory network, all right, and altering the steady state distribution, right? So again, the first method, that is reinitializing the network, the underlying network wiring is not changed, all right? So if it again gets into the bad state, it's not going to get out, right? So that problem is there. And then on the other one, that is basically a brute force optimization procedure where you're trying to change the truth table, looking at all the possible, perturbations that you can do, right? And then, by a brute force optimization procedure, trying to figure out which one is the best one, okay? So here we will do a little bit better than that. And in the way this is going to be presented, this is actually a talk adapted from a talk that I used to present about 10 years ago, right? So it is adapted from that. So we will do a little bit of review also because, we have already covered these concepts in this class, all right? But, it's introductory material for the talk. I'll go very quickly over that portion, right? And if you have any questions, you're more than welcome to stop me. In fact, if it was a different semester, I would stop with this particular chapter. But this time I think I can add in one more chapter that will give you more information about the state of the art, right? So again, I mean, this begins with a review of Boolean networks and PBNs. All right. So first you talk about deterministic Boolean networks. We already know that if you have n genes, G1 through Gn, and xi is the expression status of the ith gene, right? Then if xi equal to 0 means that the ith gene is not expressed, xi equal to 1 means the ith gene is expressed. So you have binary quantization of gene expression, right? And these Boolean networks, as I already mentioned earlier, were first introduced by Stuart Kauffman actually in the 60s, but this is a 1993 book. So let xi at time k be the value of the gene xi at time step k, and in the key defining property of a Boolean network is that the way the gene expression updates is according to the Boolean function, right? A Boolean function of the predictors evaluated at the previous time step. Okay, so in general this number will be small. It will not be going 1 through all the way up to n. Okay, it's probably going to be at most 2 or 3, right? That will decide how this gene is going to get updated at every time point. But the important thing is that the update takes place in accordance with the truth table of a Boolean function. And I have given this talk to biologists and the like. So here I just try to show them what an AND gate is, right? 0 plus 0 is 0 and so on, okay? If it's AND, then 0, 1 is 0, and if both of them inputs are 1, then you get 1, okay? So this is something that the double E's and computer science people, don't need any introduction to or explanation. Same thing with the OR gates. Right? So the evolution of each of the genes, right, is going to be given by a Boolean function. So let's define the state vector, right, which is made up of the expressions of each of the individual genes, 1 through n. So then x at time k plus 1, the state vector, is going to be given by these n Boolean functions, right, f1 of xk, fn of xk. And of course, here the number of essential variables will be much smaller because not every gene, right, directly affects every other gene in the network, right? And this is a toy example, fictitious example. So this Boolean function here, right, you could represent it either as using Boolean logic, or you could represent it as a truth table. Okay, don't give the function explicitly, just give the truth table. So here you have x1, x2, x3. In this example, 3 genes. Each of the genes could be 0 or 1, right? Expressed, not expressed. So that means there is a total of 2 to the power of 3 or 8 possible states. Okay, and if you are in a particular state, this is the predictor, right? This tells you how each of these genes will update. Gene number 1 will update according to the function f1. Gene number 2 will update according to the function f2. Gene number 3 according to the function f3. That is values that are tabulated here. And this same information, right, you can go ahead and label your 8 states, mark out the 8 states here, and draw the transition diagrams. For example, if you're at 0, 0, 0, right, in one time step you're going to transition to 1, 1, 1. That's shown here, right? So this is equivalent information. Now the important thing to note is that these 3 states, 0, 0, 0, 0, 1, 0, and 1, 1, 1, right, at the top, they form what is called an attractor cycle, because once you get in there, you keep on cycling. You go from 0, 0, 0 to 1, 1, 1 to 0, 1, 0, 0, 0, 0, and so on. Okay, and it was conjectured, again, it's not proven, but it was conjectured by Kauffman that these attractor cycles will correspond to the different phenotypes. Okay, because that's the behavior that you will see in the steady state. Okay, from the gene regulatory network, right? So in the case of cancer, it might be the tumor size, or whether it's cancer or it's normal, and so on. Now, to introduce PBNs or probabilistic Boolean networks, all right, we look at an alternative representation of a Boolean network, where now each of these binary expression patterns, right, like each xk, that vector over there, right, is basically an n-digit binary number, right, zeros and ones, all right, of size n. So there are 2 to the power of n possibilities. So what you could do is you could map each of these numbers into its decimal equivalent, right, and then once you have done that, you further so there will be decimal numbers going all the way from 1 up to 2 to the power of n, right? Then you map these guys into 2 to the power of n dimensional vectors, right, using those basis vectors, all right? And then the transition of the state will take place according to this kind of an equation, where A is a 2 to the power of n by 2 to the power of n matrix, right? And this is stuff that we have already discussed when we talked about Boolean networks, probabilistic Boolean networks, and so on. So to generalize this to PBNs, in the case of Boolean networks, the transition is deterministic. Right? If you are in one particular state, you will transition to the next state with 100% probability, right? According to those Boolean functions, right? But in the case of PBNs or probabilistic Boolean networks, the value of the ith gene at the next time step will be given by the first Boolean function with a certain probability, second Boolean function corresponding to this gene with some other probability, and so on. Okay, and the nth Boolean function corresponding to this gene with some other probability, and of course all these probabilities have to sum up to 1, right? So that's the main difference, right? And you can show that this is equivalent, right? Equivalently, you instead of having one single fixed network, you have a number of networks, right? And you can switch from one to the other. Okay, that's what happens. So if you are in Boolean network number 1, right, and you are in state 0, 0, 0, you will transition at the next time step to 0, 0, 1, right? Alternatively, if you are in the same state 0, 0, 0 in a different Boolean network, then you will transition at the next time step to 1, 1, 1, right? And at every time step, all right, the Boolean network is a new network is being chosen. That's an instantaneously random PBN. At every time step, it's like you're choosing one network among a set of networks and then letting the thing evolve from there, right? So in this case, the alternative representation of the PBN takes this form: wk plus 1 equals wk times a, where wi of k is basically the probability distribution vector. Yeah, go ahead.
How do you choose these different networks in each step? Say,
According to the probability, let's say for example, you got the predictors, okay? You got the predictors with certain CODs, for example, right? That could be one way, okay? So you could say that the selection probability of that predictor is proportional to its COD, right?
actually, a question is how you define these networks.
For that, you need to take a look at that paper. I don't have the, I mean, I could do it, but you would have to take a look at, let me see if I have the, no, wait. I'll give you the reference. You'll have to look over there, okay? But it's just an exercise in bookkeeping, okay? You're making sure that everything is, it's nothing very deep or anything like that, right? But that paper on PBNs, okay, that I will refer to later. Maybe it's a little bit, yeah. This is the paper. You need to look over there, right? It has the details of how you go from these selection probabilities to the probability associated with each network. Yeah, just look over there. In fact, somebody is presenting that. No, nobody is presenting that paper, I think so. But if somebody wants to present, they can. All right, any other questions? Oh, actually, I was on that page only where the reference was there. So here, this is the probability distribution vector, right? And A is a stochastic matrix of transition probabilities, right? Probability that at the next time step you will be at state J, given that at the current time step you are at state I, right? So this becomes what is called a standard homogeneous Markov chain, and these have been studied extensively in the 1940s, 50s, and so on. Okay, people have beaten them to death in queuing theory and other places. So we don't need new theory. Once you get it into this form, you can actually run with it. So this was done in this particular paper, Probabilistic Boolean Networks Rule-Based Uncertainty Model for Gene Regulatory Networks. So this was in 2002, right? That's where they introduced PBNs. And the stuff I presented last time, okay, about the perturbation intervention using one single gene, right? That is done in a follow-up paper, right? Also in bioinformatics. And then the stuff I presented in about altering the truth table, right, changing the steady state distribution, that is done in another paper that I think appeared in Journal of Biological Systems or something like that. All those are there on our website. If they're not on the center website, they should be on the GSP lab website. Okay, so those papers are available publicly, right, if anybody is interested. However, see, here you're doing like a one-time intervention, right? Or you're going and trying to, do some kind of brute force intervention to alter the steady state distribution. So another possibility might be to try to alter the transition probabilities associated with the Markov chain, right, using control inputs. For example, if you're looking at cancer, right, if you treat a person with chemotherapeutic drugs, all right, then the probability transitions will be different. Okay, if you treat them with radiation, it'll be different. Okay, because if there's a control action, that'll have some effect on the probability transition matrix. All right. So we wanted to see if by introducing control actions, all right, you could pose this as a control Markov chain to which you could apply optimal control theory. All right. So assume that you have m control inputs, u1 through um. All right. And again, I mean, you could have different levels, different quantization for the input, but we chose each input to be binary. So each input can take on the value 0, that is not applied, or 1 is applied. Okay, 1 would correspond to the drug being applied, 0, the drug is not applied, or therapy is not applied. And we are also going to assume that the values of the control inputs can be changed with time. Okay, this is not in these biological problems. There are additional constraints. There are other people that have done research on that. For example, if you're treating a person that has cancer, okay, you're treating them with chemotherapeutic drugs, okay, you have different constraints. You cannot, usually there is a treatment period followed by a recovery period, right? So you have to build those things into your optimization problem, right? Or, there is a limit on the dosage. You cannot give drugs too frequently, right? And then cure the cancer and kill the patient, right? That's what would happen. Okay, so there are constraints over here, right? But let's assume that this is the first paper on the topic, so none of these constraints are taken into account, right? So even in the case, so if you have m inputs and you're saying they're binary, so even the control input vector will be given by a binary number of this type, right? That has got m components. Again, you could map this binary control input vector, right, into a set of binary numbers, okay, going from 1 all the way up to 2 to the power of m, right? So the same kind of thing that we did with the states, okay? So now you have a situation where the probability distribution vector, right, is going to transition according to the equation where the probability transition matrix, all right, A, depends on the control input, right? And you want to now choose the control input to make the transition take place in a desirable way. So this is actually an old problem in optimal control, right? And that's what we used here. So the transition probability matrix depends on control input. So this becomes what is called a controlled homogeneous Markov chain, right? Or it's also referred to as a Markov decision process, right? Extensively used in operations research and other areas, right? And in queuing theory also. So this becomes now the problem of optimal control of Markov chains. And the problem becomes, how do you choose a set of inputs, nu0, nu1, and so on, to minimize a particular cost function, right? You're going to basically capture the benefits, okay, and the side effects and so on of the treatment in a cost function, right? So how do you choose the cost function? So in the beginning, suppose that the treatment horizon is finite, okay, because usually all these optimal control problems, first you formulate them on a finite horizon problem and then you let the horizon go to infinity, okay. So suppose the treatment horizon is finite and you're going to carry out the treatment over m time steps, 0, 1, 2 up to m minus 1, right? So let c sub k, right? K is the time variable here, which is a function of the state and the control, right? Zk and nu k denote the cost of applying the control nu k at state zk, right? And I mean, mathematically we can have a good problem that we can solve, okay? But in order to make this thing work, you would need input from biologists to make sure that this mathematical object, right, that you've come up with and you're calling a cost function, that really captures whatever they are interested in, right? But anyway, assuming that you've been able to find such a cost, okay, then you're doing the control over these m time steps. Yeah, it's actually not m minus 1, it's actually m time steps, right? The total cost over all these time steps is going to be the sum of these individual costs over each step, right? And then this is a random quantity because you have a probabilistic Boolean network where the transition is stochastic, even if the initial state is deterministic, right? So you are going to condition it on the initial state, right? And then you will take an expectation, right? You want to average out the effect, right? So the expectation is necessary. So this is the cost of control. So this is one part of the cost that you're going to look at, right? Now the other part is going to come from where you end up, okay? You're going over m time steps applying control. Now suddenly you stopped applying control, right? Have you ended up in a good state or in a bad state, okay? So you will put in a penalty for ending up in a bad state, right? Let's say that is causing cancer. So the net result of the control action is that the state will end up somewhere, right, in Z at time M. All right. Again, this is a random quantity. So you have to penalize the state in the cost to reduce the chances of ending up in bad states, right? For example, a cancerous state or where there's going to be metastases or something like that, right? So, and again, here you have to choose the cost that you're going to assign to these bad states. So so Cm, which is a function of the terminal state, be the terminal cost of ending up in the state Cm, right? Now you add the two costs together to get your total cost, right? So before that, how are you going to select this terminal penalty? So to determine the terminal penalty, what you can do, because once you reach that terminal state, all controls are going to be turned off, right? So you want to find out which ones are the bad states. So to determine the terminal penalty, you can set all the controls to 0, and then you look at the state space of that Markov chain, right? Partition it into equivalence classes, because remember last time I said that if the Markov chain is not ergodic, once you get into one of those irreducible chains, okay, you're going to stay in there, okay? Some of them might be bad, some of them might be good. So you are going to partition the states into equivalence classes, and you will assign higher penalties to states that are associated with rapid cell proliferation, right? One way in which cancer can occur, or reduced apoptosis. And you will assign lower penalties for states that are associated with a normal cell cycle. Okay. Again, the numbers you assign, that will determine whether your final result will make any sense or not. So you would need to get input from biologists for this to happen, right? So the total cost, when you put the terminal penalty and the cost of control together, the total cost looks like this. The terminal penalty plus the cost of control over these m time steps, take the expectation, right? So now you go ahead and assume that the control input is taking the form of a state feedback, right? So the control at time k is some function mu k of the state at time k, right? Where mu k is a mapping from the state space, right? That's 1, 2, because remember we have converted everything to decimal, right? So 1, 2 up to 2 to the power of n, right? Possible states to the control space, okay, which has 1, 2 up to 2 to the power of m. Yes, sir. Go ahead.
What's the intuition behind this assumption?
Which assumption?
The control.
You mean the state feedback?
Yeah.
Usually that's what they do, like, because in control, you have an input, all right, and you have an output, right? So when you model the system, you're going to go ahead and model it using state variables, right? And you ideally want an output feedback thing, right? Here we don't even have an output defined, right? So you want an output feedback thing, but the state feedback is easier to design. So you first design a state feedback, right? And then after that you design what is called an observer, right? Which is going to try to estimate the state from measurements of inputs and outputs. So here also we will relax this condition, okay? Because here we are assuming that perfect measurement of the state is available. If that is not available, that can also be relaxed, right? So the intuition behind it is historically people have used the state feedback, right? I mean, in the controls area, right? Yeah. So they have used the state feedback, and then of course if the state is not available for measurement, you have to be able to estimate it from the available measurements, and that also has been worked out. Okay? Not today, but in the 70s. Okay. So people have worked out all these problems. So even a lot of the problems in these gene regulatory networks in cancer and things like that, I think the challenge is connecting to the real world biology. But if you can connect it and get it into the form of one of the problems that's already solved, then the theory and all that is done. It's not like you have to work very hard. Right? Because a lot of smart people have already done the work 40, 50, 60 years ago. So, right. So this is usually what is done in control. You use state feedback and then you basically put an observer, right? Whereas in this case it'll be a little bit different, but you will understand what I'll talk about because you guys have strong background in stochastic processes. Okay, so you will understand the solution that I will talk. And in fact, today itself I will talk about that once I get done with this. Okay. So the optimal control problem now becomes you want to minimize this cost, okay, by choosing these functions mu0 through mu m minus 1, these control functions, all right? And of course these are subject to the state transition constraint, all right, the transition probability matrix constraint, okay, because that's how the state transitions, all right? This problem can be solved using dynamic programming, right, which was developed by Bellman in the 1950s, okay, Richard Bellman in the 1950s, and there are lots and lots of books on that, on this dynamic programming stuff, right? But this problem can be solved. So we are not going to spend time, trying to solve this problem because that's going to require a lot of time. Okay. Instead, I will look at a biological example that we analyzed in this context and just report the results to you. Right. So the biological example that we considered is called the so-called Winty-5A example, right? Now, and I don't know how many of you have met Mike Bittner here, right? Mike Bittner, he's at the center here. Okay, he's moved here from TGen. So at the time when we were working on this paper, Mike Bittner was at the National Human Genome Research Institute, okay, of the NIH, right? So I needed an example. I had sent this paper. This was my first paper in this area. Okay, I had sent this paper for publication, right? And we didn't send it to bioinformatics because we didn't have the actual biology example. Okay, so there was a toy example in there that was worked out, but the editor liked it, right? But she wanted a real world example. Okay, so that's when we approached Mike, and then he suggested this Winty-5A example. Now, Winty-5A is a gene that is implicated in metastatic melanoma, right? If Winty-5A expression is high, then the melanoma has got a high chance of metastasizing, right? If it is low, the prognosis is good, okay? So they had already developed part of that Winty-5A network, right, by looking at data from 31 cell lines, okay, and looking at the expression of 587 genes, okay, using microarrays. Remember I talked about COD, finding out predictors and, coming up in that. So they had already developed something, all right? So they had a closely knit 10 gene network where they use biological intuition and the methods that I talked about, the COD analysis, to develop a 10 gene network. Now it turns out that if you have a 10 gene network with ternary state space, okay, so you have a total of 3 to the power of 10 states, okay, right? I mean, each space you can have 1, 0, -1, and then you have 10 places, okay? So that was too large a state space for us to handle at that time. So we were able to reduce it to 7 genes, okay? And those are shown on the next page, right? So using the same data, right? Using the same data, and we also combined, like here you had 1, 0, -1. I think the 0 and -1, we combined it as 0, right? And 1, like from ternary quantization, we went to binary quantization in a pretty ad hoc manner, right? Because we needed to produce this example quickly to get the paper published, right? So this is the example showing the multivariate relationship between the genes of the 7-gene Winty-5A network, and these are the predictors, all right? Like you can see that, for example, for Winty-5A, you have, I don't remember exactly, HADHB and MART1, these two might be the best predictors, and there might be another two that are, and possibly maybe MART1 and pyrin also is predicting for this, okay? So some biological intuition also went into the development of this network, right? So the control objective here, because you know that Winty-5A being high means it's bad news, right? The cancer is going to metastasize. So the objective here is to downregulate Winty-5A, and arbitrarily we selected a 5-step control action, right? Because we didn't have any numbers. Nobody's given me a problem to solve, so we just said over 5 time steps. And then we had to assign the terminal penalties for the dynamic programming problem. So we said it would be 0 if Winty-5A is downregulated. All the states that have got Winty-5A downregulated, the terminal penalty is 0. All the states that have Winty-5A upregulated, the terminal penalty is 6. All the states that have Winty-5A unregulated means it's almost 1. Okay, that when you look at the ratio, they would have terminal penalty 3. Again, this just represents the gradation. Okay, that Winty-5A going from 0 to 1 is bad. Okay. So again, no rocket science here, nothing exact, right? So we looked at 2 cases. The first case is not that good, where we use Winty-5A itself as a control. Like you try, if Winty-5A becomes high, you try to force it down by using, let's say, an antibody for Winty-5A, right? So Winty-5A itself is used as a control. So send Winty-5A equal to -1, that is downregulated, and let it evolve from there to the next time step. And arbitrarily we assign the cost to use control as 1 at each time step. Then you can get the suitable decision set for all to the 2187. That's 3 to the power of 7. Okay, 2187 states at all 5 time steps by solving dynamic programming, right? So this is not very good, because it's like, the output that you want to control, you're just going directly and trying to force that. Okay, but it would still give you some benefit. Like you would like to see, how many times you really have to force things down, right? And how many times it'll automatically keep Winty-5A low without you having to intervene. Then in the second case, we use pyrin as a control gene, right? Now, how did we choose pyrin? Well, Mike Bittner suggested that was the gene to use, okay? Because you don't know which gene is going to have the most effect on the target that you're interested in, okay? So he suggested pyrin as the control gene, right? And here are a few observations from our simulations carried out with this data. When we use Wnt5a as the control gene, we could take Wnt5a to -1 in the final state. That means at time step 5, starting from any initial state. Then the probability of Wnt5a being equal to -1 is always higher with control than without control at all time points. Okay, so there is a monotonicity. At every time point with control, you're doing better than without control. And there is a need for control here because in the absence of control action, some of the initial states would transition to bad absorbing states. Like you got in there and Wnt5a is permanently upregulated, right? When you use pyrin as the control, you got a little bit weaker result because pyrin is the variable that's supposed to affect the target. So using pyrin, Wnt5a cannot be downregulated to -1 for any initial state. Okay, maybe the time window of 5 time steps is too short. Okay. So also during the intermediate steps, the probability of Wnt5a being -1 is not always higher with control than without it. That means with control, you might be doing worse while you're on your way. Okay, you're not necessarily doing better. However, for the final state, the probability of Wnt5a being -1 is always much higher with control than without it, right? And even in this case, bad absorbing states can be avoided using control. So using control has some benefit. So this was in 2003, so it's been 11 years, so it's not like we didn't do any more work after that. Okay, so there have been several significant extensions, and even these are also kind of old right now. Now the first thing to do is the imperfect information case, okay, because we are assuming perfect state feedback. If you don't have perfect information, what do you do? The second one is context sensitive PBNs, because as I said, it is biologically probably it's not correct to assume that at every time step you're going to have a new network. Okay, it's probably that the same network will continue for some time, then it'll switch. Okay, so you have to build that into your control algorithm. Then we also wanted to control a family of networks, all right, because as I said, you have to infer networks from steady state data. There might be a lot of different networks that fit the same steady state data. So if your control algorithm works only on one network, all right, that's not good enough. You want it to work on a family. And the last thing is you are interested in controlling the phenotype, so you would be interested in controlling the steady state behavior, okay, which is the infinite horizon problem, right? So all those problems have actually been worked out, right? They're all solved, and the papers are also listed here. So in the case of imperfect information, you don't have perfect information about the states. You cannot measure the states. So in that case, a sufficient statistic is the conditional probability of the state given the observation. This is an old result, okay, dating back to the 60s or 70s, okay, and people have worked on this. So you just use that instead of your state, and everything else falls into place. Of course, computationally it's a lot more intensive, because if you see earlier on we talked about the dimensionality of the state space being like 3 to the power of 7, okay. Here this is uncountably infinite because it's the probability measure of the state given the observation, right? So how do you count that? Okay, it's any number between 0 and 1. So computationally it's a lot more intensive, right? But it has been worked out, right? The second one is context sensitive probabilistic Boolean networks, all right? They are a much closer approximation to biological reality. So suppose you have n genes, then you're going to have 2 to the power of n states. Suppose you have k Boolean networks. Instead of just one Boolean network, you have k Boolean networks, all right? And at every time step, there is a probability q that you will change the network, right? And also we allowed, perturbation probability in the individual gene. Each gene can flip with a certain small probability, right? So this picture shows you, illustrates the ideas for the case where you have 3 genes. So that means you have 8 states. And let's say if you have 2 Boolean networks. So here also it is a case of bookkeeping. Okay, there are many different possibilities. You have to take all those possibilities into account to correctly calculate the transition probability matrix. Right? Once you have the transition probability matrix, the dynamic programming and all that stuff is the same as before. So here you have certain mutually exclusive events. The first one is that the current network function is applied. The PBN transitions accordingly, and the network function remains the same for the next transition. So you don't switch the network. For example, starting at 0, 0, 0, right, in one time step, you just go from here. You were in Boolean network number 1. You went to this state, and the next time step also you're going to use this network. That's one possibility, right? Another possibility is that you made this transition, but the network also switched now. So you're now in a different network, right? You made this transition, but because of context switching, you're now in a different network, right? The further evolution is going to be declared by this network, right? Then another possibility is that the transition didn't take place because of the network. Okay, there was a perturbation in the gene. One of the genes flipped, right? But you ended up staying in the same network, right? So that's this one here, where the first bit changed from 0 to 1, right? And then the fourth one is where there was a perturbation, the gene changed, and the network also flipped, right? So you ended up from here, you went there, but now further evolution is going to take place according to the rules of this particular network, right? And as I said before, we did not allow the case where simultaneously you're going to have a random perturbation and a network transition. Because then, I mean, that in one time step that both of them would happen, because I think then the math would get a little bit more complicated. But this is documented in this particular paper. And again, the main challenge is calculating the transition probabilities. Once you have that, then the rest of the story is the same as before. And here are the results from that paper. So this is the initial state number, all right? And I think for this case, we had maybe 2 to the power of 7 states, all right? Yeah, so 128 states, initial state, okay? So here we got the plot of the cost with control and without control, right? So you can see that with control, the cost has come down, okay? The red one is without control, right? So this is the expected cost for a finite horizon problem of length 5 originating from the different initial states. All right, the next topic is controlling a family of networks. So as I said before, inferring networks from steady state data is an ill-posed inverse problem. So there will be many networks that will fit the data. So you want to control a family of networks, all right? So in this case, you can come up with a control algorithm that will apply to the family of networks. And the way you do that is that the weighting of each network is adaptively estimated from the available data. Okay, so as you go along, you try to learn which network you are in, and then you apply the intervention. So that's also published. And the last one is controlling steady state behavior, right? Here you want to change the steady state using stationary control. In this case, the control, so when you let the control horizon go to infinity, all right, then you get a stationary control. That's true even in the deterministic case. I don't know how many of you are familiar with that, but linear quadratic Gaussian optimal control, if you let the limit go to infinity, all right, then the time varying control becomes a time invariant control, okay? It becomes a single state feedback. So the infinite horizon cost is considered to design the optimal control, and I'm just showing you the results here, okay? Because so in this case, it's the same example, same 25A example, except that we group together those -1s and zeros, okay, as one class, and then ones as another class, all right? So you have binary instead of ternary, so you have a total of 128 states. Now, there were 7 genes here, out of which we said that 25A is going to be the most significant bit. That means all the states starting from 63, right? So from 64 to 127, they have Win25A equal to 1. So they are bad states, okay? Because Win25A is the most significant bit. And these guys are the good states. So this is the steady state distribution that you have in the original PBM, right? So you can see that these guys are the desirable states and these fellows are the undesirable states, okay? You can see that the probability mass is higher in the undesirable states. So you go ahead and use a stationary policy using infinite horizon optimal control, and you can see that the probability mass has shifted from here to the desirable states, okay? That's what we showed here. But is this going to cure cancer? Well, there are lots of missing links here. That network has to model the cancer thing accurately, right? On paper we can show all of this stuff, but until it models that properly, it's not going to happen, right? So here is a brief recap of the different steps that are involved in modeling and control of probabilistic Boolean networks. So you have the microarray image, you have to do grid alignment, all these steps we discussed, segmentation. Then from there you have to get the gene expression. Then you have to do all the ratio tests. You have the hypothesis testing. Is it significantly different from one? Is it, upregulated, downregulated, and so on? Then from here you will do, if you use the seed algorithm, you could, pick the features, generate the probabilistic Boolean network, then formulate the control problem, and then consider all these different possibilities, okay? All these different variations of the original control problem, right? Now, for concluding remarks, okay, we know that the issue of controllability in a gene regulatory network is important, right? Because here the biologist told me to use pyrin, okay, but how do you know which gene you're going to use to control, okay? If you want to control a particular target, where should you go and intervene in the network, right? So, and this notion of controllability, it has been around in the control literature since the 1960s. It was first introduced by Rudy Kalman, right? And the standard control theory definition is there exists a control input which can take us from state A to state B in finite time, okay? If the system is controllable, all right, you will be able to find a control input that can take you from one place to the other. Because if such a control input does not exist, then you'll be wasting your time, looking for to get from one point to the other. Okay, so that is important. So the question, and I think this is important even now, which gene should be used as a modulator in the genetic regulatory network? Then the second thing is that at every step, when you're doing all these microarrays and all these other things, you are bringing in uncertainty, right? Because the robot might not have placed the spots properly, okay? Your photomultiplier tube might have different intensities. So the green dye might not be as good as the red dye, okay? So there are uncertainties at every stage. And so the technique that you develop has got to be robust, okay? So what is the robustness of the intervention strategies to modeling error? So different sources of error, noisy microarray data, discrete quantization, limited amount of data for inference. So, there are different possibilities here. You could do like a worst case design, right? Or you could do a Bayesian design. And actually this one is old, okay, like see, it's 2007. So these need to be updated. But journal papers on these have already been published in 2008, 2010 and 10 time frame. Okay, so those are available too. So. And this part actually is more philosophical, all right? In this area, this was true like 6, 7, 8 years ago. It's true even right now, okay? That it is very important to stay in touch with biology and with biologists, okay? If you just go and sit in your garage and do some math, okay, that's okay, it look like cool math, but I mean, then you might as well just be in EE and do that, okay? You should not be saying you're working in genomics, proteomics, or whatever, the real impact has to happen over there, right? So it is true that the necessary mathematical theory or something pretty close is probably available in the literature, okay? Because enough EEs and, other people in math have worked on these, mathematically interesting problems, okay? And in fact, the dynamic programming I'm talking about, that is the basis of the Viterbi algorithm. I don't know whether you're familiar with that or not, yeah. The communications engineers, they talk about the Viterbi algorithm, right? That is nothing but dynamic programming, right? So you should not get carried away by elegant mathematics, right? And there is a critical need for experimental validation of network models, right? And some of that is being done, is going to be done, right? So I think that finishes this chapter, And next time, right? Next time, what I'm going to talk about, right, on Friday, is this kind of stuff. This one stopped in 2008, 2009, 2010 time frame. Okay. Since then, also there have been advances, and the main idea over here is that if you go ahead and try to learn networks from scratch, right, you don't have enough data to learn anything. Okay. But there is a lot of imperfect information that is there in the biological literature. Biologists refer to them as pathways. Okay. These are univariate relationships, marginal relationships, okay, so they are not 100% accurate, okay. So we have worked on trying to incorporate that pathway information when you're developing a genetic regulatory network, right? That's one thing, okay, because then you need less data to learn the network. The results you get, the stuff that you develop is closer to the heart of biologists, okay. And from an engineering point, I can give you an example, like, in control engineering, there are a lot of elegant techniques that have been created by people over the last 20, 30 years. I don't know, you may have you heard of H infinity optimal control, H infinity L1? These are all optimal control methods that use really elegant mathematics, all right? But the problem is if you go out to industry, right, most people still use PID controllers, okay? The controller that controls the temperature in this room is a PID controller, right? So you can have your H infinity control, but if the final controller that you get is not a PID controller, those industry guys are not interested, okay? So many years ago, Dr. Bhattacharya, myself, and there was a PhD student, we worked on the problem of, working with the PID constraint, okay? Design an optimal controller subject to the PID constraint. You cannot get a neat closed form solution like you can get in H infinity optimal control, right? But that's the one that would probably be applied, okay, that the practitioners would be interested in. So here also is the same thing. I can create, all kinds of results, on Markov chains, control of Markov chains, and relaxing this assumption, that assumption. Biologist is not interested. You have to link it up to the pathways, okay? That's what they know. If you go and tell them your stuff is all marginal, it's not going to work, it has to be multivariate and all that, they'll think that you've gone crazy or something like that, So it's true, but you have to marry the two together, okay? So next time I will talk about that, whatever we have so far and where we are going, So basically combine prior information with observational data to come up with better models and that can and that have predictive value. Okay, that's the idea.